In this video, we will prove the Cauchy Schwarz inequality. We want to prove that a1 b1 plus a2 b2 plus all the way to an bn, the whole thing in parentheses squared is less than or equal to a1 squared plus all the way to an squared times b1 squared plus all the way to bn squared. So, to prove this inequality, we can first start with two variables to build intuition. Basically, our goal will be to prove that a squared plus b squared times c squared plus d squared is greater than or equal to ac plus bd squared. Now we can expand the left side minus the right side. So basically that will give us a squared c squared plus a squared d squared plus b squared c squared plus b squared d squared minus a squared c squared minus 2abcd minus b squared d squared. And this will equal to a squared d squared minus 2abcd plus b squared c squared, which will equal to ad minus bc squared, which is greater than or equal to 0 because it's a perfect square. So we're done for two variables. Now for n variables, we'll need a smarter approach. To do this, we can apply the discriminant proof for n variables. We can define a function of a real variable t. And we can say that f of t is equal to the summation from I is equal to 1 to I is equal to n of a it minus bi squared. This is the sum of squares, which is always greater than or equal to 0 for all real t. So if you expand this, then we'll get that f of t is equal to summation ai squared times t squared minus 2 times aibi times t plus summation of bi squared. So we're going to call this first portion here as a, the second portion here as b, and the third portion here as c. So we have f of t equals to at squared minus 2bt plus c, greater than or equal to 0 for all t is a real number. Now a quadratic at squared minus 2bt plus c that is never negative must have discriminant less than or equal to 0. So the discriminant here is equal to 2b squared minus 4ac, which is less than or equal to 0. So 4b squared is less than or equal to 4ac, and b squared is less than or equal to ac. Now we can substitute back, so we'll get that the summation I equals to 1 to n of aibi squared is less than or equal to summation of ai squared times the summation of bi squared. And that's the Cauchy Schwarz inequality. Equality holds when f of t equals to 0 has a real solution. So basically when a1 divided by b1 equals to a2 divided by b2 equals to all the way to an divided by bn. So every time you use the Cauchy Schwarz on an Olympiad, this is the proof underneath it. Thanks for watching.